to hear from you if it deviates from my list. So here's my list of 5 main results that one should be aware of. Here's the list of 5. So I'll go through these one by one briefly, just to set the stage. And the first one is about eigenvalues of a random matrix, right? So basically everything in random matrix theory, it's an exaggeration, everything, but many things center around the behavior of eigenvalues. So if you just take a random matrix without any symmetry condition, take it to be a Hermitian matrix, then, and you compute eigenvalues, then these eigenvalues tend to cluster on a circle, on a disk, which is known as the circular law, right? So this is a very remarkable fact, and this is one main result from random matrix theory that I guess everybody should be aware of. And there are many deviations, I mean, extensions and all kinds of things you can say about this, having more refined results. This is called the Ginibre ensemble. This is eigenvalues of a so-called Ginibre matrix, which is a random matrix that you construct by taking each entry independent according to a normal Gaussian distribution with mean 0 and variance 1. Okay, so that's the first main result that, okay, you should know about, in my opinion. What is the second main result? That's the semicircle law. So if you take, if you impose some symmetry on your matrix, namely that it's Hermitian or symmetric, then of course eigenvalues are real. And in this particular model called the GOE, you can construct it from a Ginibre matrix X that we had on the previous slide by adding to it its complex transpose, Hermitian conjugate. You get a so-called matrix from the GOE. And then if you plot eigenvalues, make a histogram like that, and you center appropriately, they will follow this semicircle law. Right? And this is another main result from random matrices, the semicircle law. And the semicircle law is very robust. If you take other Hermitian or real symmetric matrices with independent entries, they will, up to the Hermitian condition, eigenvalues tend to follow this semicircle law, which is named after Wegener from the 1950s. The third topic in random matrix theory that probably is not a famous result and has gained a lot of attention is about the local eigenvalues, the local behavior of eigenvalues. So if you, this was about the bulk, right? All eigenvalues, I mean, the microscopic scale. If you zoom in, say at the origin for the eigenvalues of a GOE matrix, and you do an upscaling so that the mean distance becomes of order 1, you find a pattern of eigenvalues like this, and which is, there are some features here that are important, that there are no eigenvalues that are very close. That, of course, that there's a randomness here, and they can become close, but not really close. I mean, it's very different from having independent eigenvalue. I mean, like having independent points in an interval, right? With they tend to cluster more towards each other, and there's also not very big gaps. And this universal behavior can be made more explicit. It's known as the sign. It's described by the sign kernel in the case of GOE, right? There's a so-called determinantal point process, the structure behind it, which is very prominent in random matrix theory, this notion of determinantal point process. And this is a very prominent example here, which is related to the sign kernel. So I won't go into any more details than that, but this is another thing that you may want to know from random matrix theory. And for example, and there are other connections with this. I mean, for example, if you have independent entries and you have a symmetric matrix, but with independent entries, you will also see some universal behavior of these eigenvalues that have this repelling feature, that they don't come too close, right? So it goes beyond the GUE. It's universal to a large extent. Then number 4, the fourth thing you may want to know about random matrix theory has to do with the behavior of the largest eigenvalue in a GOE. But again, it extends to more general situations. So if the largest eigenvalue is called X max, it depends on n is the size of your matrix. And with appropriate scaling, it may go to 1. But then there are fluctuations here of order n to the minus 2/3. And if you do an appropriate scaling here for the fluctuations here of this largest eigenvalue, and you think about sort of like a central limit theorem here, a like theorem for this largest eigenvalue, it turns out there's a limit law, which is given by a certain distribution function, which is known as the Tracy Widom distribution. So that's really a very important result from random matrix theory. Here you find the density of this Tracy Widom distribution. It features in Volkmar Bornemann's talk yesterday, right? And so, this is not a Gaussian distribution. That's sort of remarkable. We have new distributions coming from random matrices. This is the very famous one. There's a formula involving the Airy kernel, so there's a connection with the Airy function. And there's also a formula with a solution of a so-called Pain-Levé equation, which is a nonlinear differential equation. And that makes a connection with integrable systems, integrable ODEs and PDEs, right? So this is a very important result. It leads to many connections with other fields as well. And then maybe the fifth topic that you may want to know about if you're dealing with random matrices, in my opinion, is that there's a law for the addition of matrices in terms of their eigenvalues. So if you have large matrices, A and B, both are Hermitian, eigenvalues are real, and they're unitarily invariant, and they have certain eigenvalue distributions mu and nu, right? And then you take a sum of these two matrices. Then there's a remarkable result that expresses the eigenvalues of this sum in terms of this eigenvalues of A and B, which is valid in a limiting sense, right? When the limit of the size is going to infinity. And this is captured by this operation on eigenvalue distributions, on probability measures on the real line, if you wish, known as the free convolution. And this was first described by Voiculescu and later more explicitly by Speicher. And this gives a connection with other fields of mathematics, operator algebras, and other things. Right? So this is another result that you may want to know about. So maybe experts in the audience have some other opinion about what should be in this list of main results, but this is my list. Well, I thought I want to share it with you, just to set the stage. So in some sense, most talks will build on these, in random matrices, built on these basic results in some way or the other. And so my topic of my talk today, this work with Juan Criado del Rey, it builds on this the Ginibre ensemble, eigenvalues in the disk. And I'm talking about an ensemble of random matrices. I mean, actually, which comes about in this way, which is known as a spherical ensemble. And let's talk here. So you can make a random matrix in the following way. You take two Ginibre matrices, independent, size n by n, A and B, and you make the product A times B inverse, right? So remember that this is a complex Hermitian, this is a complex matrix, no Hermitian condition. So eigenvalues are all over the place in the complex plane. And actually, they will fill out the whole complex plane. And if you put them on the unit sphere, S2 here, by means of inverse telegraphic projection, then they become uniform on the sphere. They're still random, but they have a sort of uniform distribution on the sphere, and they have a joint density of these points then on the unit sphere, given in this quite simple expression. And that's another feature of random matrix theory, that you have, to a large extent, for many cases, you have explicit formulas that allow you to do calculations explicitly, right? At least for these basic questions. So here it's also the case, you have an explicit formula for the joint distribution, joint probability density of these, let's call them particles on the unit sphere. In terms of the distance between the all particles squared here. It's also an example of a determinantal point process on the sphere. Now, this spherical ensemble can be modified by putting some external charges on the sphere. So this model, this product of distance squared, has a built-in repulsion between these particles. Because if two particles come too close, this product here, one of these factors becomes small, right? And it gives a small probability. So particles tend to repel. Now let's assume that we have some fixed particles on the sphere, r plus one of them, and they also repel these charges, but they are fixed charges. And other charges are repelled by all of those with a certain strength A0 to AR. And let's assume that we have then a joint distribution of particles of this form, where here you see the interaction with the fixed particles, the exchange out of free particles, and the strength appear here with a factor n here. So it means that if n increases, these particles repel more and more. And then you will find the following feature, that each fixed particle of the PKs will create a region around it that's free from particles with very high probability. Right? And so we want to describe then what are these regions of free particles, and what is the remaining part of the sphere where the free particles go, which is known as the droplet. And if these AKs are very small, then these regions are spherical caps. This was proved by Brauchart, Staff, and Wormersley a few years ago, and you see a picture from their paper. But if these AKs, these strengths of these charges are bigger, then you can imagine that the blue region here, the free from particles, increases and they tend to overlap, like illustrated here. And then the question is, how can we describe this droplet? It is equivalent, I mean, in spirit, it is analogous to a model in the complex plane called a normal matrix model with external source. This is a normal matrix model without external source, where you have now points Zj are in the complex plane. Then you again see this product of distances squared here. And but now you have a confining potential here in the form of this product of Gaussians here, acting on each particle individually. This can be realized also as eigenvalues of a certain matrix model. And in this situation, this is actually the complex Ginibre ensemble. These are this is eigenvalue distribution, joint eigenvalue density for eigenvalues of a complex Ginibre matrix. And the eigenvalues fill out of this, right? That's item 1 from my list of things you may want to know about random matrices. Now, if you put some extra factors here, some extra repelling charges, now located at points qk here, again with some strengths that is proportional with n here, then you have this model with these express charges that repel the particles. And this was studied in detail for the case R is 0, so there's only one new extra particle, in the paper by Balogh, Bertola, Lee, and McLaughlin from 2015. This is this model, and because this Q repels the other particles, there is a sort of a transition depending on what the strength of this repulsion is. So if the repulsion is strong, all other particles are they don't like to become close to Q, and instead, and the semicircle, sorry, the circular law, the disk is deformed to such a moon-shaped region. But if the A is less strong, gets smaller, and there's less repulsion, and in some limit, they will go to you get a deformation of this shape, and then they close on itself, and then it will go on to having a circular, an annular region, two circles. What's also interesting in this model is to look at the characteristic polynomial, meaning in this case, you have these random particles Cj, take the polynomial that is 0 at these points, and then average over your random matrix ensemble, you get a polynomial of degree n, which has zeros, right? And in models of Hermitian random matrices, these zeros tend to behave in the large n limit in the same way as your eigenvalues of the random matrix, which are then on the real line. In this model, where eigenvalues are in the complex plane, it's a slightly different story, because the zeros of this polynomial behave differently. They go to a curve, as was proved in this paper of Balogh and company. And the curve here is indicated here with this blue line here. It's not going to the boundary exactly, because this is, you cannot really distinguish it here from the picture, but it doesn't go to the boundary, except in the critical case when these curves close when the contour closes, and also the droplet closes on itself, then it becomes a full circle. This curve is known as the motherbody, or actually the limiting distribution of the zeros gives you a probability measure on this curve, which is known as the motherbody. And so this is also something that we want to see in this spherical model. That's the goal. Okay, so let's look at this model and look at what the potential theory tells us. I mean, what we can use. So here is again this spherical model with R+1 external sources, same formula as before, same picture as before. And we look at the zero counting measure on these particles, right? Or the empirical measure, if you wish, right? So you put a mass 1 over n in each particle on the sphere, and you sum it up, and you get a probability measure. And what is known in these models is that this sequence that you have will have a limit. So there is a limit, which is some probability measure mu, which is supported here on this droplet. And it will minimize some functional coming from potential theory, which is sort of implicit. I mean, we can find it quite easily from this formula by taking a logarithm and instead of maximizing such an expression, you minimize minus the logarithm and then take a large n limit. You easily can convince yourself that you will make a connection with such an equilibrium problem, which is not this minimization problem, involving here a minimization for a measure mu with this logarithmic kernel between 2 points on the sphere, which is the repulsion that you have among the particles among themselves. And this is the influence of these free fixed charges that also repel. Some similar logarithmic terms here you find, but based at these fixed charges. And so there is a measure that minimizes this expression, and that will be the limiting distribution of these particles. Right? And the droplet is the support. And what's also known is that once you know this, the support, once you know the droplet, the density is just a constant. It's a constant density here, which is particular for this kind of models, because this is a harmonic function away from the points. Anyway, so what is this mother body? So we have this logarithmic potential for any measure, but in particular for this equilibrium measure. The mother body should be a probability measure on a curve inside the droplet that generates the same potential outside. So here's a picture, maybe it gives you a better impression. So here is this mother body. In this case, it's simply connected. And there will be a curve here that supports some measure, sigma here, creating the same potential as it is stated here, up to a constant, L, in the exterior of the droplet, on the unit sphere away from the droplet. So if you are outside, you don't see the difference. If you are here and you think about the force acting on a particle that's here, it's sort of the same up to a constant. Whether the charge would be on this droplet spread out, or whether it's concentrated here on this curve. And this is what is also the feature for the zeros of these polynomials in the normal matrix model with external source. So we would like to say something also about this mother body. If there is some symmetry here, like in this picture, you can imagine that this support here, it should be a big circle. Here, suppose here's the, and this is indeed the case, and this is one of the of our results actually. But we would like to characterize this mother body in more general situations, because we think there's an interesting phenomenon taking place. In this paper that I'll report about, which was just published this year, we do a first step with a simple, in a model where there is a lot of symmetry. So we actually consider arbitrary number of those such external charges that repel the other charges, but with symmetry. And what's the symmetry? These PJs are located around the North Pole, say in the upper hemisphere. They're on the same altitude, and they also have equal charges, and they're located symmetrically on a small circle, okay, around the North Pole. And we will actually think about this after the calculation that we do in the complex plane. So we're actually going to move this problem from the sphere to the complex plane by means of stereographic projection. So the North Pole is mapped to infinity, and the South Pole goes to 0 with this stereographic projection. And so here you see a picture then in the complex plane. This point here corresponds to the South Pole, it's the origin. And here you see 3 circles or disks, which inside here are the projections of these fixed charges. In this case, R is 3. I took 3, sorry, R is 2. So I took R plus 1 is 3 such external charges. And they project onto 3 points here inside these disks, not quite the centers. And this corresponds to the situation when the charges are small. This number A is small, so that these 3 regions around these charges are spherical caps, which then project onto these disks with stereographic projection. And if you increase this number A, you can imagine the following, right? And this is actually what we can prove. So if this is the picture from before, if this number A increases, then these disks will grow, right? They become bigger. There's more repulsion from these fixed charges. The other free charges are moved away. And then at a certain point, you have three disks that these disks become tangent. And because of the symmetry, they all become tangent at the same value, right? Then this is the region in the southern, around the South Pole, that's still occupied by the charges. And this is the region around the North Pole, which looks bigger, but is actually smaller. And then if you continue, these three disks, they grow into each other and they get deformed. There's a new shape here coming in. But there's still a piece around the South Pole, around 0, that's occupied by the charges, and a region around the North Pole. And if we assume that our points are in the in the Northern Hemisphere, which we will do, then if we increase further, then there's this next transition when this region around the North Pole disappears. And we only have this region around the South Pole that remains. So now this is on a different scale here. This is actually what remains, which corresponds to this picture here in the middle, actually, right? So it's on a different scale. This is, and there's nothing left in the outside. So you can see these sort of three regimes with some transitions between them. This is what we would like to capture. How do we do it? Well, what we do is we first concentrate on this mother body. Well, first, we go to the complex plane by this stereographic projection. Then there's still this symmetry, this R+1 fold symmetry that comes from the model. And to state the results, I first want to undo the symmetry. So if we take an R+1 fold exponent here, then this shape here, R is 2 in this case, so you map it with, becomes a shape like this. And the mother body, these three pieces here, will become a segment from 0, this is 0 here, to some positive number, right? And so this sigma, which is the mother body measure, right, which we're going to characterize it by means of a vector equilibrium problem, which part of the solution will be the measure that we get after these transformations. So first to the complex plane by stereographic projection, and then undoing the symmetry so that we come to this piece here, or in the other pieces, it can be the full half line or two intervals on the half line. And we do that by means of a vector equilibrium problem. That's what we were able to do. It involves these notions, again, from logarithmic potential theory. This is some double integral that we already saw, but here with two measures, mu and nu. And if I write it with mu, if I just write I mu, then I just mean that mu and nu are the same. So this is our equilibrium problem that we found. So it involves an R tuple of measures. So that's why I call it a vector equilibrium problem. Mu1, mu2 up to mu r. Mu1 will be the main character. So let's keep that in mind. There are several terms here, as you see. This is just the energy, logarithmic energy for each of these measures individually. This gives an interaction between mu j and mu j plus 1. So you see that in consecutive measures here come into play. And because of the minus sign, it means that these consecutive measures in this vector, they attract each other. because of the opposite sign here. And then there is some extra term here acting on mu1, some potential V1 acting on mu1, and a VR acting on mu r, which is the last one. And these are external fields of this type. And V1 is some number t. There's two constants coming into play here, t and q, that ultimately will correspond to the location of these points given by the number q, and t is related to the strength A in a certain way. This gives some interaction, repulsion from a point at minus q inverse here with the measure mu1. That sort of, again, is it attracting piece here. And there's another, this VR gives you some attraction because there's a minus sign here with some other point, but for the measure mu r. Okay, it is okay. I cannot give you any really good intuition for why this is going to play to play a role. Okay, you have to believe me. I cannot go into the proofs, I'm afraid. So I'll state the result, and then. So this is the energy functional we want to minimize for a vector of measures. But where are these measures? Well, these measures are on the real line, but they alternate between the positive real line and the negative real line. So mu1 is on the positive real line, mu2 is on the negative real axis, then back to the positive real axis for mu3, and so on. Okay, that's another condition we put. And then there is this condition about the total masses. The total masses have this property. They come in some arithmetic progression in this way. If j runs from 1 to r, so if j is 1, you have 1. So mu1 is a probability measure, but the other measures are they have bigger mass, right? They increase it like this, which is sort of new to me. I've never seen a problem where the masses are increasing. There are other vector equilibrium problems that I've seen where the measures actually go down along an arithmetic progression. They go up is sort of a new feature that I've seen in this model, but not before. Anyway, so what are the results we have? Well, there's a unique minimizer. That's the first result, but this is actually there are quite general results about the existence of minimizers, and so this is a special case of that. So we could go to the literature and have that. This first component is the main guy, the main feature. At the end of the day, we have a long proof, but at the end of the day, our conclusion is that if you go back to the sphere, right, it will give you the mother body sigma. So what do? The mu1 is on the positive half line. You map it to this r plus 1 half rays, right, just undoing the symmetry. And then you map it back to the sphere by inverse geographic projection. Then you get this sigma. So the sigma will indeed be supported on these meridians. But what is, that's the good thing. The mu1, there are only 3 cases for mu1. It's either an interval from 0 to x1, or a union of 2 intervals, one unbounded and the other containing 0, or it's the full half line. This is on the assumption actually that q is bigger than 1, or maybe q inverse is bigger than 1. So that the points is in the upper half plane, in the northern hemisphere. The other measures, the sort of secondary measures, they have full support, either the negative or the positive half line. So our proof also uses a lot this function. This is a function you can create out of this measure mu1 once you show an existence and show these properties about the support that we do with potential theory. We consider this function phi, which is here some Cauchy transform of this function, and then some explicit rational function with a simple pole at minus q inverse. This turns out to be an algebraic function, meaning that it satisfies an algebraic equation of order R actually. And this will be important for us actually, for the proof. And we can show that this equation here, if you ask yourself when z times phi is equal to some expression involving z, and the number r is, again, r plus 1 is the number of external charges, this defines a closed contour or a union of closed contours. And it encloses a domain U. That's another thing which is essential for us. And this will then give us the droplet. So in this case, where the mu1 is supported on one interval from 0 to x1, then this droplet, this U may look like this. This will be a bounded domain. In the case where the measure mu1 is supported on two intervals, this is maybe the most interesting case, then you have this situation that U has two components, one going around the first interval and one around the unbounded interval, which is an unbounded domain here. And if the mu1 is supported on the full half line, then this U is an unbounded domain containing both 0 actually and infinity. Okay, and then this is then the rest of the theorem that we have, that this domain U will then give us the droplet. After going back to the sphere, right, as before. And for a certain model, right, a certain model of these external charges, P0 to PR, what are these charges? Well, they are equidistant around the North Pole, and they project onto points in the plane with this radius. So we assume that Q is less than 1. So this number is bigger than 1, and the charges are related to the number T that you find here. They have the same charges. The number A is related to T in this way, which is a positive number. If T is 1, then you get A is 0. If T is getting close to 0, you get A big. And so this is the result I want to present here. I cannot say about the proof. My time is up actually. So there's more potential theory. That's actually the main tool we use. There's some ideas from balayage to show that this vector equilibrium problem has a solution and that it has these supports. And we use the algebraic function phi and its Riemann surface. And there's a change in this Riemann surface depending on the situation. And this middle situation is actually a genus 1 situation. The Riemann surface has genus 1. This is genus 0, genus 0. So this is a more simple situation. And so this is a phase transition that we could see on the level of this, on this algebraic geometry part of the problem. So I cannot go to the proof more than that, but let me thank you for your attention, and thanks to the organizers again for enabling me to talk to you about these results. And